Okay, hi everyone, and welcome to the May MAPP webinar. This is Dan Barry. I'm joined in the room by Ken Mooney and Rick Rosen, also of Climate Program Office. Today, the topic of the webinar is intraseasonal to interannual prediction, and we have 5 speakers. We're going to hear from Ben Kirtman from the University of Miami, Vasu Misra from Florida State University, Kathy Pijan from NOAA Earth System Research Laboratory, Dwayne Walliser from NASA Jet Propulsion Laboratory, and Matt Newman from the Earth System Research Laboratory also. The format of the webinar, we're going to hear each of these 5 talks, and in between there will be time hopefully for some questions. If we're left over with time at the end, we can have additional discussion if anyone is interested. So Ben, are you on the line?
Yeah, I'm here.
Okay, great. I'm going to transfer control over to your computer now.
Okay, so I'm going to talk about how the NMME prediction system captures the diversity of ENSO.
So Ben, have you brought your slides up on the screen? Sorry.
I sure do.
Okay, great. I think we're a little bit lagged here. You know, like it seems like the lag has carried over, so just keep that in mind.
Sure.
Okay, thanks.
Coming up yet?
Yep, it looks good. We're on the outline NMME slide.
Perfect. So I'm gonna start out by giving a very brief description of the NMME system, talk a little bit about the diversity of ENSO in the NMME system, and as some of you may know, there's a sort of this ongoing debate about whether there's a continuum of El Niño events, whether there's Central Pacific El Niño events versus Eastern Pacific El Niño events, and there's a whole lot of different names for these, Modoki and so on and so forth. So I'm really sort of taking an agnostic view, and I'm going to be looking at a couple of specific events and just going to look at how well the NMME system captures those specific events and the differences between them. This is really event-based. We're going to look at precipitation also, not just SST, because one of the arguments about this diversity of ENSO being important is that the teleconnections associated with the different El Niños are very different, and so precipitation, precipitation distribution in the tropical Pacific is really a good, or at least a pretty good indicator of how there might be different teleconnections. And then the last thing, if I have time, which I think is highly unlikely, I was going to show you a little bit about some work we've been doing with North American rainfall during the 2006-2007 Southeast drought. The second slide that I'm showing you here is just a table. I'm using my cursor here so you can see. It's just a table showing the various participants in the NMME system. I will just make sure I'm clear, these 2 models, the 2 IRI models, they provide hindcasts, but they're no longer participating in the real-time activity. Again, just to get you oriented on the kinds of things that the NMME system is producing, this is a time series of observed and predicted Niño 3-4 temperatures. So the black is the observed evolution of Niño 3-4. The top panel is 1982 through the end of 95, and then the bottom panel is 96 through 2010. The black, of course, is OBS. The red is the ensemble mean, and the gray curves is the distribution of all 100 ensemble members. So, or order 100, I think it's 106 or something like that. But order 100 ensemble members, and showing you at 1 month lead or a half-month lead, depending on how you look at it, the NMME system is capturing the evolution quite well. When you go to slightly longer leads, this is the same format as before, but now this is looking at the 6-month lead, and not surprisingly, the ensemble mean shown in red is in somewhat less agreement with observations, yet still the major events and even some of the smaller ups and downs are captured by the ensemble mean. And you can see the gray curves show the uncertainty. So if we take, for example, the 1986-87 event, you can see that there's not necessarily agreement on all the ensemble members on even the sign of the event. And in fact, you can see in the ensemble mean, this red curve, you can see the ensemble mean dips below 0 well before it did in observations. Yet the observations do remain within the plume of the gray ensemble members. The next slide, I'm hoping you guys are, the internet is keeping up with me, but the next slide shows the ranked probability skill score for the NMME system versus in comparison to CFS v2. And so these are the July 1 starts, and this is DJF SST verification. And it's important to note that in this metric, we're treating every single ensemble member equally. So if a model produces more ensemble members, it has greater weight on this particular metric. So we're using each ensemble member equally to resolve the probability distribution. And what you see in comparison to the NMME system in comparison to CFS is you have a lot more reds, which is good. Reds is good, and red are good, and blues are not so good. So it's increasing the amount of red and decreasing the amount of blue. So even on a nice probabilistic measure of forecast skill, the NMME system is doing quite well. So now getting to the diversity of ENSO, this is just now I'm picking a very, very short lead. So I'm really giving the NMME system here the real benefit of the doubt, and I'm looking at a specific case. So this is forecasts that were initialized the early part of January, so the first 5 days of January, so verifying January, February, March 1995. And so the top panel shows the observed structure, and the bottom panel shows the ensemble mean from the NMME system. And so in a broad brush sense, the model is the NMME system is capturing the fact that the asymmetry between the east and the west, that the largest anomalies are occurring near the dateline or just to the east of the dateline, and not necessarily trapped at the eastern boundary in terms of our canonical view of ENSO. But you can also be quite critical of the NMME system in the fact that it's producing warming near the eastern boundary or the eastern Pacific that's really not showing up in the observations, at least in the ensemble mean. And this behavior of warming for these events that seem to occur more out to the west, this is really a consistent behavior in the NMME system. The models want to produce warming in the east right away. They do capture this east-west asymmetry, but they do produce too much warming in the east. So this is another way of looking at that with a little bit more of a quantitative measure. And so I'm going to start by talking about the bottom panel, which is showing you the spatial structure of the sea surface temperature anomaly right at the equator. This is just average 2 north, 2 south in this particular picture. And the blue curve here is the structure of the NMME ensemble mean. The gray are each, the 100 different ensemble members, and the red curve here is the observation. So you can clearly see that actually in the eastern Pacific, the observed lack of warming is just about, if not out of the plume. So the models really do have what I would argue is a systematic problem of producing too much warming in the east for relatively short lead times here. The top panel is the pattern correlation, and so this pattern correlation is computed from 140 east to 80 west, 20 north, 20 south, and the red dots, the red plus signs is the pattern correlation of the SST for the NMME system for each individual ensemble member and the observed observed SST. The blue is doing exactly the same pattern correlation for rainfall. So overall, you can see, it's generally the pattern correlation is around for the SST, maybe 0.5 or slightly less than 0.5, and there is some quite a bit of uncertainty. There are some models. Each plus sign is a different model. So you can see there are some models that are these are clustered around the same model, relatively weak pattern correlation. In here for short leads, relatively high pattern correlation, and so on and so forth. The next figure, again, I'm hoping you guys are rapidly catching up with me, is the SST pattern now for JFM 1998. This is the famous El Niño of all El Niños, or at least the most recent one. And the top panel is the observed, again, for those short leads. And the bottom panel, again, is the NMME ensemble mean for those short leads. And so in this case, you can see the model looks fairly good compared to OBS, but the signal is very, very large, and that's certainly an important point to make. And then the next figure is showing you the same as before, the individual ensemble members, in gray, the NMME ensemble mean in blue, and then the OBS on the bottom, and then on the top is that pattern correlation. And you can see that across all the models, that pattern correlation is always greater than, for the SST, is always greater than 0.75. The blue is interesting, and that's the pattern correlation for rainfall, as I mentioned before. And you can see, for example, this cluster of models here at the beginning is really struggling to get the pattern correlation for the rainfall. And you can see there are other models that sort of struggle quite a bit in getting the pattern of the rainfall correctly, even for the 1998 event, when you would expect us to do quite well. So sometimes these teleconnections are going to be difficult. And this is just an example of the rainfall distribution. And I don't remember if I included, this is the 95 case. I don't know if I remembered to include the 98 case, but what you can clearly see is this is the observed rainfall, quite relatively weak for 95, but really very much pinned in the central or western Pacific. And the NMME system is typical, and this is typical of the NMME system, to get a stronger rainfall signal than observed for these events that seem to peak out further into the west. So a fairly strong rainfall signal in the NMME system. And again, you can see it extending perhaps too far out to the west. Oh, then here's the rainfall signal. I did remember, so good. The next picture is the rainfall signal for the 98 JFM 98, and you can see the nice big signal, and the model's doing a fairly good job of capturing the distribution of that. Okay, so just moving on, I'm going to talk a little bit about the North American rainfall. This is some other work we've been doing with the NMME system. And so this is now looking at precipitation over North America, and these are the July 1 starts, and this is again that RPSS scale metric, so again using all order 100 ensemble members. And the top panel is the NMME system, and the bottom panel is CFS V2 for comparison. And again, what you can see is we've reduced the amount of blues and enhanced the amount of red, and all of that is very good. And in fact, all this, one of the nice features for me in particular is a lot of this enhanced skill over Florida, that actually is in large part due to the model that we're contributing to the system. That's a big contribution from the NCAR model, actually. So I got my 12-minute notice from Dan, so I'm going to skip this slide because it would take too long to explain, but I will go to this second to last slide. This is actually looking at that 2006-2007 drought period, and the first column here is looking at the rainfall distribution from observations for February, March, April 2006. August, September, October 2006, February, March, April 2007, the observed drought you can see in browns. And then you can see the NMME system forecast at 1.5-month lead, doing a fairly good job in 2006, capturing some signal August, September, October 2006, and rather anemic in 2007. The interesting one is then when you go to the 6.5-month lead and you look at the bottom panel, and we're actually, that February, March, April 2007, we're totally getting the wrong sign. And I'll go to my last figure, and you could get the drought completely wrong just because perhaps it's unpredictable or there's lots of noise, but it does actually look like this is in the same format, but this is now the SST forecast as before. What it does look like is that the NMME system, if you look at the bottom right corner, in that FMA 2007 season, is producing erroneously large, warm SSTs for that particular season, and it's giving you the canonical ENSO response there. So it might be that that drought is unpredictable, but the NMME system perhaps missed it because of a bad SST forecast as opposed to necessarily having too much noisiness in the rainfall forecast for significant predictability. And I'll end there. Thanks.
Great. Thanks a lot, Ben, for the excellent overview of NMME progress. Are there any questions here in the room for Ben? Okay, I'm going to go to the phone line. If everyone on the phone could please check to make sure that you're muted, unless if you intend to ask a question, that would be appreciated. Are there any questions on the phone line?
Yeah, this is Ray with a question for Ben. It's a real interesting point you brought up here in your last slide. I wonder if you have any plans to do companion experiments with observed SSTs so you can try to sort out how much of the error is due to the SST forecast versus model dynamics in the response to ENSO.
This is exactly, I have a student who's produced these last 3 figures. That's exactly what her PhD proposal is to try to sort this out and determine whether that busted, or at least part of her, whether that busted forecast can we blame on the busted SST part, or was there actually some predictability, or are we suffering from a signal to noise problem? That's one of the specific tasks as part of her proposed research. So yes.
Great, thanks.
Thanks for the question, Ray. Any other questions on the phone line or in the room? Okay, great. Thanks a lot, Ben.
Sure.
Vasu, are you on the line? Hi, Vasu, are you there?
Yes, I'm here.
Okay, great. I just switched control over your computer, so just share your desktop, please.
Sure, thanks.
Okay, looks good, yeah.
Hello, good afternoon, everyone. This is Vasu Mishra here from Florida State University. I would like to acknowledge 2 of my colleagues, Professor Zhaohua Wu, who provided the SST forcing for this seasonal hindcast produced at the Florida Climate Institute. It's at 50-kilometer grid resolution. It's a 2-tiered forecast. And also Dr. Hai-Chin Lee, who actually conducted the seasonal hindcast integrations. So I'll be comparing the forecast results from this 2-tiered forecast with the NMME models. But before I do that, I will go ahead and explain what went in this FISH 50 hindcast. So the objectives are laid out here. I'll describe FISH 50, talk about the deterministic forecast results, the probabilistic forecast results, and compare FISH 50 with NMME models, and then specifically in the last slide, look at the Asian monsoon. FISH 50 has been done for the period of 1982 to 2008. Plans are to update it to 2012 for both winter and summer starts. The seasonal hindcasts have been initiated in the first week of May and June. of each year for the summer, and last and first week of November or December of each year for winter. Each seasonal hindcast has 6 ensemble members. We have updated it to now 12 ensemble members, but I'll be showing you the results only from 6. Each seasonal hindcast is for a duration of 6 months. It's a global spectral model run at T248, approximately 50 kilometer resolution. There are a couple of new features in the physics. We use the Kane-Fritz scheme, which is not often used in at least the NMME models. And it is at a resolution which is slightly higher than what is being done at NMME. So the FISH 50 is at a relatively higher resolution compared to the NMME models. We use slightly different model physics than the rest of the NMME models, especially the cumulus parameterization scheme. I will not have the time to discuss about the sensitivity to the cumulus parameterization schemes to the seasonal hindcast in the stock, but it does have a dramatic effect. Two-tiered system is forced by multi-model CCSM3 and CFS-V2 average sea surface temperature anomalies. Both of these models are part of the NMME suite. Bias correction of SST is done in a very unique and effective manner, and I'll describe that in the next couple of slides. The perils of conventional bias correction of SST for forcing AGCM is, in fact, it inflates your hindcast skills. But before I explain that, I should tell you what conventional bias correction is in my lexicon. The hindcast period here is 1982 to 2008, and if you replace SST climatology, say CFS-V2 hindcast from 1982 to 2008 using corresponding observed climatology, then I would call that as the conventional way of bias correction. And this conventional bias correction is in fact in some ways cheating because you are using the observed climatology from the forecast period or the hindcast period. And so you tend to most likely inflate the hindcast skill, and when you go in operational real-time forecasting, it is possible that you may not be able to match the hindcast skill. And if you wanted to avoid doing this conventional downscaling, conventional bias correction, you could use the 27 or 28 years prior to the hindcast period to replace the model climatology. So for example, you could, but before I show that, I would like to show the systematic errors of CFS-V2 and CCSM3. On the left panel, you will see the CCSM3, CFS-V2 systematic errors of SST. There's a cold bias in DJF in the equatorial Pacific, and in MAM, which is one season lead, you have a warm bias in the eastern equatorial Pacific. And in the CCSM3, the cold bias persists in both seasons, DJF and MAM for the winter starts. And if you move to the summer starts, you see the cold bias persistent in both the seasons. So the systematic errors in both these models are pretty large, and if you are trying to use these SST forecasts, I think it becomes pertinent to get rid of this systematic error. But what if you assume that the mean global SST is stationary and then conduct a bias correction? In other words, you use the previous 27-year periods, like using 1955 to 1981 to do the bias correction. So you take the 1955 to 1981 observed SST climatology to replace the hindcast climatology of the two models. And if you do that, you introduce a severe cold bias of the order of almost 0.5 to 0.8 degrees centigrade in the tropical oceans, which is pretty large. So what we have done in FISH 50 is we have used a new SST product called SST sub F, which is equal to SST OLF, which is the observed low-pass filtered SST, which includes secular trend plus decadal variations. In fact, we do this low-pass filtering and we pass anything with a period of approximately 40 years or more. We obtained this SST OLF from 1881 to start of the seasonal hindcast, and it is updated every year. And this filtered SST is persisted through this 6-month hindcast period. The SST MME is the multi-model forecast SST anomaly from CFS-V2 and CCSM-3, and the SST A cycle is the stationary climatological annual cycle that is prescribed. So when we use this SSTF and then compare it with the observed climatology for the period 1982 to 2008, we see that the errors are far less and is probably acceptable in a 2-tiered forecast like FISH-50. So I'll jump into the results. I'm showing you the correlations, a deterministic way of looking at the ensemble mean seasonal precipitation anomalies from FISH-50 in the top panels for DJF and MAM, June, July, August, and September, October, November. And in the middle panels, I'm showing the corresponding correlation skills from CFS-V2, and in the bottom panel, I'm showing it to you from CCSM-3. I'm comparing right now with these two models because this is where we got the SST anomalies to force this FISH-50. And the regions where I have circled are the regions where I feel that the FISH-50 is complementary to the other two models. For example, if you look over Southwest United States, the skills are well over 0.7 correlation, which is far higher than what CFS-V2 and CCSM-3 shows. But there are other regions around the globe where the skills in FISH-50 are probably less than what is displayed in CFS-V2 and CCSM-3. So certainly FISH-50 offers some complementary skills compared to the two coupled models, both in all 4 seasons. If I look at the probabilistic skills, which is measured as the area under the relative operating characteristic curve for terrestrial seasonal precipitation anomalies for oceans on the left panel and over land for the winter hindcast, what is clearly seen is that FISH-50 is the probabilistic skill of FISH-50 seems to be comparable to most of the NMME models. There is no significant deterioration of the skill just because AC coupling is neglected in FISH-50. It is largely comparable, and most models, in fact, at least in terms of precipitation anomalies, seasonal precipitation anomalies, seem to suggest that all these models are comparable, at least over the oceans. If you move over the land, again, the skills are relatively comparable, but slightly less than what is displayed in the oceans. One interesting aspect is that the middle terrestrial anomalies are harder to predict. The models tend to go to the extreme terrestrials more often than desired, both over the oceans and land. In fact, over land, the middle terrestrial is very hard to predict by any of the models. Again, over land as well, FISH-50 shows that it is not inferior to most of the NMME models. In fact, there might be regions where it is slightly superior than many of the NMME models. If we look at the seasonal surface temperature anomalies, once again, we do see that the middle terrestrial anomalies are harder to predict. The extreme terrestrials have got higher skills, probabilistic skills. But in contrast to the precipitation skills, there is a larger spread in the skills amongst the NMME models, and you especially seen in June, July, in the boreal summer seasons than in the boreal winter seasons. especially in this panel here, June, July, August, in the global mean temperature, you can see there are some models which have skills in the range of about 0.55 versus about 0.65 in some of these models for the extreme terciles. So there is a larger spread in the surface temperature skills than in the surface precipitation skills. And if I go to the Asian summer monsoon, we looked at both the South Asian monsoon region and the Southeast Asian monsoon region. I have not outlined it, but the South Asian monsoon region is largely the Indian domain, centered over the Indian monsoon, including the Bay of Bengal and Arabian Sea. And the Southeast Asian monsoon is centered over China, which includes the parts of the Western Pacific Ocean and the South China Sea. On the right panel over here, what I'm showing you is the distribution of signal-to-noise ratio for the June, July, August mean precipitation. On the x-axis is the signal-to-noise, which is basically the ensemble mean anomalies divided by the ensemble spread. And this is the frequency distribution, or rather the distribution of the number of points with this kind of a signal-to-noise ratio with these two domains. This is over the ocean points in the South Asian domain, and this is the land points in the South Asian domain. And you can see CCSM3 seems to be overtly confident over the South Asian monsoon oceanic regions compared to the other two models, Fish 50 and CCSM3. On the other hand, over land, it is far less confident. Likewise, over South China Sea, most of the models are far less confident over Southeast Asian monsoon compared to the South Asian monsoon, both over land as well as over ocean. If I then look at the distribution of the correlation of the seasonal precipitation with respect to the signal-to-noise ratio, then we clearly see that there is some skill. That means when the signal-to-noise ratio is pretty high and if the correlation is pretty high, then the model seems to be rightfully confident about its forecast. And although the correlations are hovering around 0.2 and 0.3, it is a bit gratifying to note that at higher signal-to-noise ratios, the correlation skills are relatively higher over the South Asian monsoon. However, if you look at the Southeast Asian monsoon region, it's a slightly sobering result. The ENSO signal is not as strong, and I'll get to why we think Fish 50 is doing slightly better over the Indian monsoon region. Most of the skill is largely coming from the remote ENSO forcing over the Indian monsoon region, and this is shown as the Niño 3.4 SSTA anomalies and the ensemble spread of the seasonal precipitation anomalies from Fish 50, from CFS V2, and CCSM3. And in both these coupled models, the ENSO forcing is very weak over the South Asian monsoon region compared to Fish 50, at least over land. You can clearly see the strong ENSO forcing. The red points are ocean, the black points are land, and you can clearly see there is a very strong ENSO forcing that is preserved in Fish 50, while in CFS V2 and CCSM3, it is just not there. And if you look in the Southeast Asian monsoon region, there is again very strong ENSO forcing over the South China Sea. I'll stop here because I've got my 15-minute notice, and then leave the conclusions on the screen. Thanks.
Okay, great. Thanks a lot, Vasu. Are there any questions here in the room for Vasu?
Yeah, Vasu, this is Anarita. I was just curious to know whether you have used Fish 50 in a forecast mode, for example, comparing with NMME over the 2011, 2012.
No, I have not used it in. We are just about to begin updating it to 2012, but we have not used it in a real operational mode.
Thanks.
And I go to the phone line, please mute your phone unless you have a question. So are there any questions on the phone for Vasu? Okay, great. Well, thanks a lot, Vasu, for the presentation.
Thank you.
Our next speaker is Kathy Pijon. Kathy, are you on the line?
Yes, I am.
Okay, great. I'm going to switch control over to your computer.
Okay, can you see my screen?
Yeah, looks good.
Okay,
so whenever you're ready, go ahead and get started.
All right, sounds good. What I'm talking about today is forecasting forecast skill, and I'm going to do that in the context of an ENSO conditional skill mask, which I will explain in detail throughout the talk, and try to see if applying such a skill mask can be used to improve seasonal predictions. And this is work that I've done in collaboration with Arun Kumar at CPC. Okay, I have tried to advance the slide, but it's not going.
Try giving it a click with your mouse the first time. Left click.
Okay, yep, that works. All right. So the first question you might have is, what is a skill mask? And my definition here, I'll go into detail how CPC uses it, but what I'm doing here is calling it a simple model for forecasting forecast skill. And the skill mask that's used at CPC, an example is shown here on the screen, and it's just the average historical anomaly correlation skill determined from the CFS V2 reforecasts. And so on the left side, you see an example CFS2 2-meter temperature forecast that was initialized in June of 2012. And that's the actual full field forecast. And then on the right, the skill mask was applied. So everywhere where you see gray, the average historical anomaly or correlation skill is less than 0.3. So the model's forecast is considered not skillful. So basically, in this context of this skill mask, it's the past performance is indicative of future performance. It's assumed that the past skill of the model represents the future skill of the model. So what we'd like to do is to maybe be able to do better than that in terms of applying a skill mask. So maybe we can produce a more sophisticated forecast of forecast skill. So I'm going to do, in terms of this, is to develop a skill mask conditional on ENSO, and I'll be using the CFS V2 reforecasts at 0, 3, and 6-month leads for temperature and precipitation, mostly focused over the U.S., although I'll show some global plots as well. And we're going to do this in a perfect model context where we withhold one ensemble member as truth, determine the skill using the other 23 members, and repeat that for all members. So the first thing I'm showing you here is that since I'm in a perfect model context, whereas previously what I showed you from the CFS2 was in actual verified forecast, this shows you the average correlation skill from the CFS2 in a perfect model context. So this is for 0-month lead, temperature on the left, and precipitation on the right, and I'm showing it for 4 different seasons. So this just gives you an idea of what the skill is in perfect model world, and it's certainly, if you compare this to actual skill, the value of the skill is higher, and of course precipitation is more skillful, temperature is more skillful than precipitation. So this is just the baseline of the average historical skill and the average skill mask, and now we want to see if we can improve on that. We think we probably can improve on that because skill varies highly from year to year. And as an example of that, I'm showing you in the upper panel here. This is the fraction of land area where the anomaly correlation skill is greater than 0.5 over the U.S. And that's for each year and season. And you can see that that skill has a lot of variance. The middle panel shows you this same sort of quantity based on the average skill. And then the bottom panel is a ratio such that everything above 1 is where the skill for that season and year is greater than the average skill, and everything below 1 is where the skill for that season and year is less than the average skill. So we might assume that if we're using the average skill mask, we're missing out on some of these high skill opportunities. So what we want to know is, can we predict the skill associated with an ENSO signal? We're going to do that with a simple linear regression model, where we try to forecast the forecast skill in terms of anomaly correlation as a function of season and year. And we do that with an index of ENSO, and I'll show a couple of different indices of ENSO, one being the absolute value of Niño 3.4, and the other being the absolute value of some principal components from tropical Pacific SSTs. So we think it makes sense that this should be possible because the skill of temperature and precipitation over the U.S. Is highly related to the signal of ENSO. So this just shows you an example that that is true with the normalized noise, which is the ensemble spread on the bottom, or on the x-axis, and the normalized signal, or the ensemble mean, on the y-axis. And then the colors are showing you that the regression coefficient M here as a function of season that shows us the relationship between an ENSO index and the skill of temperature, or on the top, precipitation on the bottom. And as you see, as the signal increases, you have a stronger relationship between ENSO and skill. And that's true for precipitation and temperature both. So we expect that we should be able to do this based on what we know about ENSO and its relationship with skill of temperature and precip. So now to show you how this regression model works, this shows you the regression. This is the actual, in space, that regression coefficient between skill and Niño, absolute value of Niño 3.4. And wherever you see red, there's a strong relationship between ENSO, the ENSO index, and skill. And so, for example, in March, April, and May, in the spring over North America, we see quite a lot of quite a strong relationship. We also see that in precipitation, and this kind of makes sense in the areas where we would expect there to be high skill associated with ENSO. Now we're also considering some other indices of ENSO as part of creating this skill mass or regression model to forecast skill. We consider the possibility that a fixed in space index like Niño 3.4 may not actually capture the seasonal evolution of the pattern of the SSTs, and therefore its teleconnection. So what we've done is to try using principal components from seasonal EOFs of SSTs as our predictor. So for example, if we look at the December, January, February EOFs, we see that the first EOF is what we might expect as the canonical ENSO. And the second EOF comes out as we think either a trend or some decadal variability. There's only 28 years to this Pinecast data set, so it's very hard to be able to say for sure whether it's decadal variability or trend. And then also, it's been shown or demonstrated in some ENSO diversity work that there are different teleconnections associated with the Central Pacific ENSO. So to capture that, that would be the third EOF. So as an example of that, I'm showing the regression relationship between the skill and the absolute value of that first PC. And again, that first PC is seasonally varying. So you see for each of the seasons, again, the relationship is strong where between that PC1, which is, again, an index of ENSO, and the skill in a number of places that we would certainly expect. I didn't point out last time I showed you the previous regression plot, but there are certainly regions where the skill, these blue areas, show you where the skill is actually higher during ENSO neutral. So keep that in mind, that could sort of mess up an attempt to predict skill based on relationship with ENSO. So just to be clear about this PC1 and how different it is in its relationship with skill versus a Niño 3.4, I'm showing you in the upper right here of each of these plots RMS difference and a correlation to give you an idea with the regression relationship from Niño 3.4. So this tells us in terms of amplitude and pattern how similar using PC1 as a predictor is to using Niño 3.4 as a predictor. And you can see that in most cases they're very similar, although as we get to precipitation in December, January, and February, there's some differences. And there's also some distinct regional differences that I won't go into in this call. So now that I've described our different ENSO predictors, I want to show you how well these predictors fit the data that we're trying to fit them to. So we're trying to predict the skill of the temperature and precipitation forecasts, and this is telling you how well these predictors are fitting that. So again, since it's a fit, it's not cross-validated. I'll show you the forecasted cross-validated ones in a minute. But what you see here overall is that each of these predictors, Niño 3.4, PC1, PC1 plus 2, or PC1, 2, and 3, all fit better in terms of fitting to the forecast skill than using the average skill. And that's true for 0, 3, and 6-month leads for temperature and precipitation. So that's a good indicator that we're doing the right thing. But the important part here really is how well do each of these predictors forecast skill. And this is showing you the RMS error when you actually make a forecast and cross-validate. And when you look at this, you see that for the most part, it's these green lines. It's the dashed, which is PC1, and the green solid, which is Niño 3.4, which have, for the most part, the lowest, the lowest errors. Although you see quite a lot of times the average model has very similar values as well. The largest errors come when we add in the other higher order PCs. So it seems that potentially using Niño 3.4 PC1 might help to improve on the skill. So if we get to the fundamental questions we were asking here, do ENSO conditional mask improve on the average mask? And the answer here is no. It's very hard to improve on the average mask. And so I'm showing you this in terms of differences in high key skill score for winter. And since I'm getting short on time, I'll just show you, make it clear that wherever you see blue, it means that the average mask is better than any of our ENSO predictor based masks. And so you see, for the most part, average does better than trying to use the ENSO conditional mask. And then the second question we're interested in really is, does including these additional PCs improve the skill over Niño 3 as a predictor? And this is a difference in high key skill score for temperature. And the answer, these are very noisy differences, and the answer really is that these additional PCs, such as including the trend or decadal variability or Central Pacific ENSO, do not in any systematic way improve. So the conclusions are that including the additional PCs to represent the trend or decadal variability, as well as Central Pacific variability, doesn't offer any systematic improvement over Niño 3.4. And really the key conclusion is the ENSO conditional skill mask does not improve on the average mask. And I didn't have time to show this, but we think this is due to the fact that using an ENSO conditional skill mask produces many more equal chances forecasts. So really the takeaway message here is that it's hard to skillfully forecast the forecast. Thanks.
Thanks a lot, Kathy. Are there any questions here in the room for Kathy? Okay, I'm going to go to the phone line. Any questions on the phone?
Yes. Siegfried.
Siegfried, let me just, if everyone else could check to make sure that they're muted, it would be appreciated. So Siegfried, go ahead. Reaching for that mute button, yes. All right, Siegfried, you still there? Siegfried, Siegfried, you there? All right, Siegfried, are you there?
Hello?
Yeah, hi. Okay, go ahead with your question. Sorry about that.
Okay. It's not a question, just a comment. One of the things we found is that it's the interference between the different ocean basins that sometimes plays a role in the predictability. So, Kathy, you might want to consider looking at some measures of what's happening in the Indian and Atlantic Oceans.
Okay, thanks. That's a good idea, Siegfried.
Any other questions or comments for Kathy? Okay, thanks a lot, Kathy.
Thank you.
Dwayne, are you on the line?
Yes.
All right, I'm going to transfer control over to your computer.
Okay, do you see the first slide?
Not yet. You should go up to the share menu and then share your desktop.
All right.
You may need to bounce back into the event center. Okay.
Now?
All right, looks good. So whenever you're ready, go ahead.
Okay, thank you. So pleased to be able to present this ISV hindcast experiment on behalf of Ben, who would have liked to have been the presenter, but he had another commitment that he had to attend to. So he asked myself and Junyi to help put this together, and Junyi should, and I expect also, is on the line. And so this first slide really illustrates all the contributors to this experiment, and I'll describe it in more detail in a second, but the map there is showing the institutes that have contributed hindcasts and the control simulations to the experiment, and the blue ones are more or less the operational centers that have contributed, and the gray ones are other research institutes. And the list of names there acknowledged, along with Ben, there's another set of names there that about 3 or 4 years ago got together and tried to sort of be the initiative behind pulling this together. And unfortunately, along the way, Junyi Lee was hired at IPRC to really take the reins of this, and she's done most of the analysis and data caretaking so far, and is really one of the chief principal contacts for getting data and knowing all the details about it, and done a significant amount of work in working with all those partners. And another person there I'll acknowledge is Nina Manny, who's a postdoc who started here about 9 months ago, and I'll show a few of the results that she's put together recently. And then there's the team members, which are mentioning the people there in the map and contributing the model output, and I'll show those in more detail in a second. And then along the bottom are various sponsorships at different levels, including the sort of programmatic ones of Amy and Yahtzee and Clivar and APCC, who actually I think contributed something financially. And then the thing that really got this off the ground in terms of analysis was a proposal that Ben led along with a few others of us to the NOAA Climate Testbed Program, and that's sort of what's actually manifest actual results in this, and so we're appreciative of the support that NOAA gave for this. So I'll go on to the next slide. I won't read this in detail, but the real motivation for this was for those of us interested in MJO and related ISV predictions. There had never really been a real good hindcast data set for up until the occurrence of this hindcast data set. There was always, for at least a decade or more, many hindcast data sets that were motivated by seasonal prediction, and they just never were workable for MJO forecasting, for example. They would either start only at the beginning of the month or the beginning of the season, or save monthly output, or for a variety of reasons, they just never had the right set of constituent sort of guidelines that would allow you to study the MJO and other related ISVs. So this is really the first coordinated hindcast experiment that's really suitable for looking into multi-scale variability associated at the intraseasonal time scale, and for looking at forecast scale and studying predictability. And that's the background and where the emphasis came from, and it had support, like I said, from a number of different programmatic entities listed there at the bottom. So the experimental, so the objectives are on the next slide, and there's a number of them that can be cultivated out of this experiment, and really the model output and so forth really just has come together in the last year, so there's much more to be mined from this than the few initial results you're going to see today, and there's a lot more opportunities for people to utilize this, and so hopefully through this talk today it'll motivate some more people to get involved. So with the model output and the experimental design, there's ways of looking into just the basic physical processes of intraseasonal variability, the MJO. There's certainly the wherewithal to look at potential and practical predictability, which is really one of the main foci of the experiment objectives. And another one on top of that, which was also used to motivate the climate testbed proposal, was to look at strategies for developing MMEs for ISB prediction, looking at model deficiencies, physical mechanisms, and another thing is just multi-scale interactions between the various weather through seasonal climate variability. So those are the things that can be garnered out of this data set, and you'll see we're just starting to make progress on a few of these, but there's much more that can be done. On this slide, it shows just the high-level experimental design, and roughly speaking, there's two types of experiments. There's a control simulation from the experiments, which are designed to illustrate what the intrinsic variability is within the model, and also to study multi-scale interactions that might involve annual and interannual timescales or smaller timescales, including weather. And so those are typically just 20-year runs, and the experiment has contributions from both coupled OGCMs and forced AGCMs, so there's no restriction there. And then the second part is really with the hindcast data set, which the specifications there are in the table, and for the most part those have been followed by the contributors, and that there's about, every contributor's done about 20 years of hindcasting, and the forecasts are all 45 days or longer. We've tried to get at least 5 members for each one, but you'll see in a minute that those are hard to adhere to by every organization. And the nominal ask was to have this every 10 days on the 1st, 11th, and 21st of each month. But for the most part, especially for the operational centers, this hinged on utilizing what system they had in place, and not everybody does it the same way. So those aren't adhered to strictly. And then in terms of model output there at the bottom, the specification calls for a number of atmospheric fields, and there's both quite a few two-dimensional fields, for example, at the surface and at the top, and then a few at mid-level, and then some 3D fields of some of the prognostic variables as well. And then there's even a few upper ocean variables, including profile data up to about 300 meters for a few things, for the case of the coupled models. And then on this slide, you can see who has participated and contributed, and thanks goes to all those people who have spent time in making their runs available and getting them to Junyi, and IPRC has acted as the host in this in an institutional way, and it's a great help in that regard too, to have a central focus for all the data. I won't go over those in detail. You can see the contributors there. And now this slide shows the description of the models and the experiments, and so there's about 10 coupled models, and you can see that the Australians, the Canadian, ECMWF, GFDL, JMA, the Operational Center, and JAMSTAC separately. NCEP has contributed actually two different sets of hindcasts, as ABOM has as well, both a version 1.5 of POAMA and 2.4. SNU has contributed hindcasts, that's Seoul National University, and then IPRC itself through Joshua Fu. And in that case, the control run often relies on a CMIP-like run. The period is very close to being the same 20-year period, and you can see the ensemble size differs from 10 in a few cases down to 1 in one case. And the initial conditions, that's the thing that varies by quite a bit, makes the analysis a little bit challenging, but still possible to meet the original objectives. And then there's a couple cases of a two-tier system there at the bottom, the Central Weather Bureau from Taiwan and MRDEC. I can't think of what that is, maybe ECM. And so those are the people who have contributed, and all that model data has now been sent, and it's being analyzed. So now I'll just highlight a few of the results that Junyi has taken on and been doing for at least over a year or so, and has 1 or 2 papers in process. And I'm going to mention that the modes for analysis, we've been largely discriminating up to date between the MJO for boreal winter and boreal summer ISO, which we call BASISO, or that's what Ben and Junyi often refer to it. So the analysis that you're going to see in terms of prediction skill and predictability are going to be based on the RMM1 and RMM2 indices, the well-known Wheeler and Hendon indices for the MJO. And the pictures there are just a schematic to remind us all again what those are. So we're looking at the principal component of the time series of those projections as they're projected onto the model forecast. For the summer case, we're using two other modes that have been developed by Junyi, and she's worked on trying to develop a set of modes that we can use for monitoring the boreal summer ISV variability and for predicting it. And she's done that in concert with the MJO task force. So many of you know, about 4 or 5 years ago, the MJO working group at the time, and then the task force developed a metric from the Wheeler and Hendon indices that now operationally the centers send their forecast data to, and that in turn there's a web page at CPC that shows the forecast of the MJO based on those indices there at the top. And we wanted to do something similar for the boreal summer. That was one of the objectives of the MJO task force. And so because the RMM1 and RM2 are not super ideally suited to look at the boreal summer intraseasonal variability, so Junyi took up the challenge to try and come up with some modes that would be descriptive in terms of boreal summer intraseasonal variability associated with the monsoon. And what's shown here are those two, in this case, two modes. So meaning 4 EOFs. So the first the top row there is EOF1 and EOF2, and those are two EOFs that describe a propagating mode, the real common one that we associate with the Asian Australian monsoon. It's got a tilted rain band from the northwest to the southeast, and that thing propagates intraseasonally and sort of makes up part of the northward propagating variability of the monsoon that we would like to predict. The second mode on the bottom, EOF 3 and 4, is the second BASISO mode, and that's also a fairly other well-known mode that the tilting is in a slightly different direction and it comes in from the western Pacific, and so that's captured here too. So again, the time series for each of these are used in the subsequent slides in terms of assessing prediction skill and predictability. And that construct of that mode is written up in a paper that's been accepted with the Junyi led, and it's out in press and possibly in print now. And just to show you what those modes account for in terms of fractional variance, on the left side, what these plots are showing are the fractional variance accounted for by the RMM indices, the two-component RMM indices over winter for OLR, U850, and U200 there. And it's on the order of, say, 30% or so. And these are just the variance of the anomalies, just taking out the annual cycle and interannual variability, but otherwise it's just 5-day means. So there's no additional filtering done. So the variance captured in the winter from the Wheeler-Hendon modes is on the order of 30 to 40%. And on the right side, it's showing the fractional variance accounted by those 4-component BASISO modes in the summertime, and it's on the order of the same amount about. Going on to the next slide is actually the first real analysis of the prediction skill from this hindcast data set, and this is in preparation right now by Junyi. And some of you might have seen these results before, but what it's showing is the forecast skill in terms of the correlation coefficient, the bivariate correlation coefficient of the RMM. Oh, I'm sorry, this is just RMM1 on the left and RMM2 on the right, so it's a single score there. Correlation coefficient of those time series versus lead time. And the blue lines there is the mean of all the different model prediction skills, and the blue vertical lines are showing the spread. And then the red line shows an MME based on the 3 sort of best models. And in this case, it's the ECMWF, JMA, and ABOM2 contribution. So a single ensemble of 3 of the models, and that's the skill of those. And you can see that the skill using 0.5 as a threshold goes out to about 3 to 4 weeks, which is substantial and a good thing for those of us interested in this problem for a long time to see that evidenced here. And so changing to the summertime, go to the 4 modes that I described just a few minutes ago, and you can see it's the same illustration here. Now the first mode has a forecast skill out to about a lead time of 3 to 4 weeks, shy of 4 weeks, and that second mode is significantly curtailed down to 2 weeks. And then looking at the bottom 2, you can see that the skill isn't quite as far out for those higher frequency, sort of higher wave number type fields, which is to be expected. So you can see overall the wintertime mode has a forecast skill from these models in this configuration in terms of a hindcast of about 3 to 4 weeks, and then in terms of this summer mode, anywhere between about maybe 2 and almost up to 4 weeks. So these are forecast skill measures, and I'm going to just change gears a little bit to look at predictability, which is another one of the objectives from this hindcast experiment. This is work done by Nina Mani. She was a graduate student actually with Goswami and has come here, like I said, about 9 months ago, and this is in preparation. So these are measures of MJO predictability from each of the models. And what's shown in any given panel, the red line going across the top is just a measure of the variability associated with the MJO in terms of the RMM indices. And so that's just a measure of the signal. And then the blue lines are the RMS error in predicting those from a predictability experiment, and it's just the model measuring the model or assessed against the model. So in any given case, one ensemble member is considered to be truth, and then it's measured against that. And so in this case, you can see the predictability measures which occur or measured out to when the error and the signal match are anywhere between 3 to 4 weeks, and CFS2 is even significantly longer, out to 39 days. That's the one in the lower right. And so there's a substantial amount of predictability there from the models when used in terms of just measuring predictability and measuring themselves. If we put these together all in one slide, this slide shows the gap between any given model's assessment or estimate of its predictability and the prediction skill. So the black bar reaches up to the point where it measures a deterministic prediction skill of a single member. And then the gray bar shows the enhancement of using the ensemble for that given model. And then the yellow bar goes up to the point of measuring what that model would give if it was used to just measure the predictability of the MJO. So you can see most models certainly can improve, not to be it's sort of expected, but at least a week or more is still remaining out there in terms of reaching the predictability limit, at least as measured by these models. And this is a figure to just demonstrate how well in these model ensembles the forecast error matches the ensemble spread. And in some sense, it would be ideal if the ensemble spread matched the forecast error spread, and it doesn't quite happen in that case. In almost all cases, the ensemble spread is about half of what the forecast error spread is. The closest and best model performance in that regard is for ABOM2, which is the red line. It actually comes, the red solid line, which is the ensemble spread, almost comes close to the ensemble mean forecast error spread line there. And so that's how far most of the research has gotten in terms of prediction skill and predictability estimates. This lists some of the activities going on. And so I talked about one and illustrated these prediction skill estimates that Junyi is carrying out with Bin Wang, and you saw here the estimates of prediction skill for the MJO and BASISO modes. Another thing that they're working on is to look at just intrinsic modes of variability within the coupled system in this experiment. You saw a few results from the MJO predictability study that Nina is helping lead. She's also going to look at the prediction skill of ISV over the Eastern Pacific. A number of you know that Shannon Zhang, who also works with us, has spent quite a bit of time over the last 5 years or more studying intraseasonal variability in the Eastern Pacific and its connections to tropical cyclone behavior and so forth. So we're going to try and look at the prediction and predictability of ISV over the Eastern Pacific in conjunction with Shannon. Another activity, Net Johnson leads the prediction of MJO teleconnection patterns. And then this last one of many maybe are things that you'd like to see done. And if you can think of things to do with this data set, please contact Junyi and Ben and propose something. The data's there, and it's quite a resource. It's something that hasn't existed up until now. So welcome your collaboration on this. Thank you.
Great. Thanks a lot, Dwayne, for giving the presentation on Bean's behalf also. We have time for one quick question. Anyone on the phone or in the room?
Dwayne, this is Rick Rosen. Yes, this is quite a gold mine, the data set. In the arena of many more things to do, are you aware, independent of the MJO work you were just showing, are you aware of anyone who's looking at how well high-impact events over North America might be captured on the 2-week to 3-week prediction by these models?
That could be part of number 5, but I don't know if he's focusing on just large-scale indices like PNA or AO, or if he's actually looking at specific extremes. But I think it's a good project, and this would be a nice data set to help mine that from. And for those of you that are aware of the S2S project, there's a nice complementary aspect here between this being very retrospective and in terms of a hindcast data set, and S2S will be prospective. And so together they are a nice set of resources to help look into the problems like that. And the one you just suggested, Rick, is a really good one.
Thank you, Dwayne.
All right. Thanks a lot for the talk, Dwayne.
Thank you.
All right, Matt, are you on the line?
Yep, I'm here.
All right, I'm transferring control over to your computer.
All right.
All right, whenever you're ready.
Is it working?
Yeah, it looks good, Matt. Whenever you're ready.
Okay. All right, so I'm going to be looking at just trying to understand, trying to see if I can, to some extent, forecast the forecast skill of atmospheric anomalies. I'm not focusing on the MJO per se, just anything on this kind of subseasonal time scale, looking at 5-day running means. And we're basically using a multivariate red noise kind of empirical model. So you can see it's essentially the same kind of form as univariate red noise, except now X is a series of maps. And one can determine L using the linear inverse model technique and then make forecasts with this kind of equation. Obviously, you don't know the noise, so your forecast will degrade in time. So here we're going to use as a state vector, like I said before, 5-day running mean, SST, OLR, and 208.50 millibar wind anomalies in the entire tropics. And essentially this is kind of constructed on a 5-day lag, just kind of like an AR1 model, and you can test it on much longer time intervals to see if it's a reasonable model. So there's a lot of tests one can do, and I'll just kind of give one as an illustration. This is looking at the spectra of tropical SST monthly anomalies, so this is like ENSO, and basically if you look at that, you can see that with the observed in pink that the limb, which is constructed on a short lag, is able to reproduce this kind of spectra essentially out on ENSO timescales and much shorter, and it's doing it basically as well as GCMs can do as coupled models. And there are other tests one can do and show that it essentially reproduces observed evolution on these timescales as well as models. So it's a useful thing both for forecasting, and then it's a lot simpler than a full GCM, so it's easier to try to diagnose predictability. Now, in the context of predictability, what we're basically looking at is essentially a signal-to-noise ratio. So without getting into all of the math, that's kind of the key thing. We're looking for structures which we can diagnose actually from this dynamical operator that we've determined from the data. We're looking for these structures which grow most rapidly over a certain period of time, and those will tend to be the structures that are most predictable, although one can derive essentially an expected anomaly, an expected skill for essentially any forecast. All right, so this is an example of a structure which grows most rapidly over a 20-day time period. So in other words, this is the initial condition, and the shading here, I'm showing an OLR anomaly and 200 millibar winds, although obviously there are other fields as well. And this evolves in the context of the limb in this way. So it's essentially OLR is amplifying over 20 days, and obviously in this case the winds are as well. And so this then might be expected to be the most predictable initial condition for a 20-day forecast. That's basically the idea in the limb. And you can see that this is actually a relevant structure, because if I project data on this pattern and then 20 days later project it on this OLR anomaly, I get this scatter plot. So basically there is a pretty good linear relationship that one sees in observations, and in fact it grows the way you expect it to. That dashed line is essentially that expectation. All right, so what we're going to do then is we're going to look at all the forecasts that are initialized with a fairly large, either positive or negative, just to simplify things, a large anomaly, essentially a 1 sigma projection on this initial condition, and then we'll just see what the forecast skill really looks like. So that's essentially what's shown here. My measure in this case is a pattern correlation of an OLR anomaly from 60 west to 60 east, so essentially the entire tropical Indo-Pacific. And I'm just doing the pattern correlation between the observations and the observation and the forecast. So the blue bars is indicating the average of all the forecasts, or hindcasts in this case, cross-validated hindcasts for the limb, for forecast leads of 5, 10, 15, 20, 25, and 30 days. So you can see obviously in the blue scale obviously going down as you'd expect with increasing lead. And similarly on the bottom I'm showing the same thing in blue for the CFS2. So at early leads the CFS2 has much higher scale, and then as the lead gets longer the limb basically has a higher scale. But the key idea is that this stratification is working for both the limb and actually for the CFS2. So what I've done is I've separated out the forecast scale only of those cases which had a high initial projection on this growing structure, and that's in green, and then all other cases are in red. And you can see there's a very large, and it's so large it's, with these cases it's statistically significant. You have a large, much larger forecast scale in these high singular vector, these high growth cases, than when you don't. So the difference is like 0.2 at long lead in terms of the mean skill. And you see that even with the CFS2, even though overall the skill is less, again, we're still picking out those cases which are more skillful from those cases which are less. So this is giving us a way of identifying what initial conditions might be in an a priori sense leading to a more skillful forecast. And it's a fairly simple idea here that the growth of the anomaly, this amplification that one can identify in the limb, is what's giving rise to this greater skill. So we can go a little further. Because we have SST and these atmospheric variables, we can actually try to quantify to some extent what the effect is of the anomalous coupling here. And so what we're essentially doing, again without worrying about all the math, is we're going in and we're turning off certain parts of the operator. And if we turn off certain parts of the operator, it turns out we can decouple the system. So we can have kind of an SST portion that's internal SST and an internal atmospheric portion. That's essentially the idea here. And it turns out that if you remove coupling, as you might expect, it has a very big impact on the interannual variability, but it turns out it has almost no effect on intraseasonal timescales. And the reason why is that even if you don't decouple the operator, you can find that there's actually two separate, distinct classes of dynamical eigenmode subspaces in this linear dynamical operator. In other words, there's a set of essentially a set of eigenmodes which act to evolve in a fairly slow, so they have a very low frequency or stationary, and are very persistent. They have a long e-folding time. So you have this class which is evolving and in a slow manner, and it turns out that if you compare these eigenmodes to the uncoupled linear operator, you can show that this class of eigenmodes essentially are very, very sensitive to the coupling between the atmosphere and the ocean. So when you decouple them, then the decoupled eigenmodes look very different from these eigenmodes here. Conversely, there's another class of eigenmodes which it turns out are representative of much faster variability, not nearly as persistent, so the e-folding time is quite a bit shorter. And it turns out that these eigenmodes, when you decouple the operator, look very similar to the decoupled atmospheric-only component. In other words, this class of eigenmodes are a form of space that essentially are not very strongly impacted by coupling to SST. They're primarily internal atmospheric modes, as it were. So we can use this very nice separation, which just comes out of the original linear operator. In fact, we don't even have to worry about doing anything to it. We can just look at these two spaces, and we can essentially split up any anomaly on any given day in terms of this coupled space and what I call this internal subspace. And you'll notice, and this is kind of an important issue, that these two subspaces, although they're separate, they're not orthogonal. So in practice, what that can mean is there can be a structure in a coupled subspace, say, which has somewhat of an MJO shape to it, kind of a positive minus with a sort of horizontal scale. And there can be a similar shape in the internal subspace, and they can overlap. Okay, so in this coupled subspace, that shape, that MJO structure, might actually have might not really be the MJO. It might have a 200 or 300 day period and much longer e-folding time. But it'll look like this MJO structure which evolves on, say, a 40 to 50 day time scale. So that's going to be an issue later on as we try to identify how important coupling versus not coupling is, say, to MJO predictability. All right, so here's an example of how this works in practice. So what I'm showing here are two Hub-Mullers, one both for the year 1998, one set for SST, one for OLR. And this is the total, and so running down along the equator, you see a warm event changing to a cold event, and here's kind of the OLR anomaly that existed at the same time. And I can apply this filter, and if I apply this filter, which just by essentially a spatial projection, what I find, as you might expect, is that most of this SST variability is in this coupled space, whereas most of the OLR variability it's kind of spread out. So a large part of it is kind of this ENSO evolution, so it's much slower. And then there are these small ripples going through MJO or other intraseasonal variability. So I can kind of separate skill a little bit. And here I'm just going to show the skill stratified by projecting initial conditions in the context of the limb now, either only on the coupled space or only on this internal atmospheric space to start, and then just see how the skill varies. And what I find, and it's not really maybe too surprising, is that early on, there's actually a little greater skill if I only had the internal atmospheric component and initialize my forecast with that. But as forecast leads get longer and longer, basically that internal atmospheric component doesn't give me a big increase in skill. Most of the skill I'm now seeing is coming just from this coupled space. All right, so at least by my clock I'm at 12 minutes. So
exactly.
Just to conclude, so what I'm trying to show here is that basically we can use these limbs to diagnose predictability because the skill is competitive with these GCMs and because it's able to reproduce variability. And what we're finding basically is that there are these two separate spaces. There's essentially a coupled space, which is more predictable, and an internal atmospheric space, which is essentially less predictable. And so it's going to be tricky then to try to identify a pure MJO-like skill. In fact, to some extent, maybe that's not a well-posed problem, because some of these MJO structures are going to essentially appear to be operating on fast time scales, but there will also be some MJO-like structures which are actually operating on slower time scales as well. And so separating that out becomes kind of a research problem. But the key thing here is that the subseasonal forecasts do appear to have skill which may be predicted ahead of time based on this kind of signal and noise idea that one can determine from the limb. Now, in the limb, of course, there's no spread skill relationship. So fundamentally, we don't have to worry about variations essentially in spread. All we need to do is look and see what initial conditions are giving rise to greater amplification, and that alone can give us a distinction between what forecasts we expect to be skillful and what do not. And so the plan is to kind of continue working on this, testing it out, and institute these kind of forecast-to-forecast skill in this forecast page, which runs in kind of a quasi-near real time. Okay, and I'll just conclude there.
Great, thanks a lot, Matt. Are there any questions for Matt? Anyone on the phone line with a question for Matt?
Yes, I actually have one. I'm Cecile Penland. You say there's no spread skill relationship. How exactly are you defining skill and spread then?
Well, the spread is in terms of the, if you go all the way back here, the spread is going to basically be in terms of this integrated noise, right? As you know, I have the statistics for that. It's a function of forecast lead, but it's not a function of individual state. So when we think of spread skill relationships, usually the idea is a different forecast state might have an ensemble which has a bigger spread, and then another state might have one which has a smaller spread.
Well, I agree. It's state independent, but that's not skill independent.
I'm sorry?
I said I agree that it's state independent, but I don't think the spread is skill independent.
No, it's kind of the other way around.
We can talk about this later.
Yeah.
All right.
Okay, thanks, Cecile. Any other questions for Matt? Okay.
Yeah, Matt, this is Anarita. I was just wondering if you could elaborate how you envision this kind of limb forecast skills being used, potentially useful for folks who are, who have to forecast operationally.
Yeah, I mean, that's part of what this project is about in the next couple of years, is talking more to operational people. I mean, in the context of this, what I'll do is I can essentially predict, come up with my prediction of what I expect the skill, say the anomaly correlation will be, and just put it on the forecast. But I think the thing to do, obviously, is I'm going to have to, use the limb, use this to derive essentially an expected skill using a measure that people are more comfortable with. So probably something on the order of these Heidecke scale or RSS kind of measures. But I think that's that's going to be something that I'm going to hopefully work out over the next year or two.
Thanks, Matt.
Okay, thanks a lot for the presentation, Matt. Appreciate it. And thanks to all of our speakers, all 5 of our speakers today. It was a pleasure to hear about your progress on your projects. We have one more webinar left in the series. It's on June 11th, Tuesday, June 11th, and the topic is tropical climate extremes. And there are 5 speakers for that webinar session. Also, we're going to hear from Jae-Kyung Shem from CPC, NOAA CPC, George Hallowell from NOAA Atlantic Oceanographic and Meteorological Laboratory, Gabe Vecchi from NOAA GFDL, Yolan Sarah from University of Arizona, and Chunzai Wang from NOAA AOML also. So thanks a lot to everyone for joining, and again, thanks to our speakers, and I hope you join again next month.